Welcome to lecture 15 of CSE 31. So in this lecture, we are going to talk about a new topic on program process. Okay, so before we start, there are some announcements. Okay. Project 1 is due the Friday after we come back from spring break. And after the due date, starting from the following week, you have 7 days to demo your project to your TA. So don't demo it before then, because I will need to give rubrics to your TAs for the grading. Okay. And there's a new homework. Homework 4 is online. Make sure you access homework 4 through CAT courses. Click on the links from CAT courses. It will direct you to Zybox, and then make sure you click the submit button, because if you don't click the submit button, I won't see the score. And sometimes if I log into Zybox and I may not see your progress at all. So make sure you follow the process. Otherwise, you may need to redo your work. And there's a new reading assignment, and it's due Monday, the 6th of April, which is in 2 weeks, or the week after we come back from spring break. That depends on when you watch this video. And we're going to have a new topic probably in 2 weeks. So yeah, make sure you read the textbook. Okay, so in the last lecture, we pretty much covered the conversion between MIPS as well as the machine language. And we know that MIPS contains 3 formats: R format, I format, and J format. And based on the opcode, we can tell which format they are. So make sure that you look at the MIPS reference sheet and then find out what the opcode is, and then you can determine the format. And we also talk about true assembly language. What does that mean? True assembly language are instructions that can be converted into zeros and ones directly. And if you have an instruction that cannot be converted to machine language or machine code directly, that instruction is called pseudo instruction. So any assembly language program that contains pseudo instructions are considered as MAL or MIPS assembly language, which means that one or some of the instructions are pseudo, and you need to break it down into multiple true assembly language instructions in order to be converted into zeros and ones. Okay, so starting from today, we're going to talk about the process of program, which means that starting from you writing a C language, a C program, how does it go down to CPU and have the CPU understand it? So this is what we call program process. And in this lecture, we're going to cover several topics. First one is the difference between interpretation and translation. They all sound the same, right? But actually in computer science, they actually means different things. So we're going to talk about that. And then we're going to talk about the process of translating C program. Okay, what does it take for the CPU to understand the C program that we write? And it involves compiler, assembler, linker, and loader. So probably we will talk about linker and loader as well as some examples in the next lecture. So today's lecture, we're going to just focus on the translation and interpretation as well as compiler and assembler. Okay. So when we write the program, how is the program run actually? So well, our program is written in the source code, right? So how does the computer actually run the program? And there are 2 ways to run a program, depends on what programming language you're using. So the first one is called interpreter. Interpreter is the program itself. So basically, when we write a program in an interpreter language or interpreted language, we are actually executing that program with another program called interpreter. So the interpreter actually is executing the program that we write into machine code. So this is called interpreter. And it happens during runtime, basically. And the second way to run a program is called translator, which means that before we run the program, actually the translator will translate our program from our source code into a hardware or machine specific code. Okay, so for example, the machine code. And now when we run the program, we are actually running the machine code. So this is called translator. So an example of interpreter is scheme program, or sometimes if you know MATLAB, it is also an interpreter language, which means that you need to have a program to run your program, basically. Okay, so for example, if you write a program in MATLAB, for those who have taken numerical analysis, so you need to install MATLAB in order to run those M files. Okay, so, and the conversion or the translation happens during runtime, and that's why it's called interpreter. Okay, so for example, scheme program. You write a program called full, and as you run the program, actually the interpreter, the scheme interpreter is running behind the scene and try to translate the scheme program to zeros and ones at the same time. So basically, in order to run a program, you're actually running two programs. Okay? And as I mentioned, the program is actually happening during the runtime. And Java as well as Python is kind of like hybrid. When you compile the program, you compile that into bytecode, as we kind of mentioned at the beginning of the semester. Okay, so, and you save the Java program, right? So you have something .java, and then you compile it, and the Java IDE will convert that into something .class, and then, or JAR, okay? And now, in order to run that program, JAR, you need to have Java and runtime environment. And when you run the program, the Java and runtime environment will do the interpretation in runtime to translate the JAR code into machine code. So Java and Python are considered as hybrid. It's compiled interpreted language. So you do the compilation beforehand, but when you run the program, actually the interpreting mechanism actually still running behind the scene. Okay. So what about translation? So C and C++ are translation language. So we need a compiler to translate a program from C language to machine code. So which means that when you do GCC, this is what's happening. Okay, so when you type GCC, it will convert our C code into something .out, right? Or an executable. And executable is essentially the machine code. So now once we compile it, as long as we don't change the source code, we can reuse the machine code all the time. So we can just keep on typing / and then full .out. Now you get to run your program all the time without recompiling it. So any reason why we want to use interpreted language then? Okay. So, well, if you think about our Merced, okay, so because it's an interpreted language, because there's no way we can write assembly language with our own computer, otherwise it makes our computer vulnerable, right? Because you can actually control the CPU directly. So we have a simulator to interpret our assembly language into machine code in runtime. Okay. So what is good about it? One way to do it, one reason why we have that is that because it's an interpreter, we can also insert a lot of debugging information, okay, into the program. And then as we have bugs in our program, then the debugging information will clearly tell us what the bug is. Okay, so it's a lot cleaner. So if you think about Java, right? If you encounter any exception or error, Java programming language or the environment will always give us a more detailed error code. For example, array index out of bounds. But if you compare that to C, usually if we have array index out of bounds, what does C compiler give you? segmentation for. So it doesn't really make sense to you, right? But that's the way, right? If we have an interpreter language, then we can incorporate this kind of detailed information into the interpreter program. And during the runtime, if something happens, the program can handle the error nicely. The other one is that is when using interpreting language, it allows us to convert programs from one machine to another machine, or from one generation of a machine to another generation of machine. So that happened when we used to use Apple computer, like Macintosh machine. We don't really call that Macintosh anymore because we call that Mac PC or MacBook. Okay. So what happened? So long time ago, Mac computer used Motorola CPU. Okay, so Motorola 680, that's really old CPU. And they have different architecture. And then later on, until like probably 20 years ago, they switched to PowerPC. And PowerPC actually was manufactured by Motorola, but in conjunction with Apple, but the architecture was totally different. So in order to make the switch, and what happened is that the program itself has a simulator. What it does is it interprets the program from the older generation CPU to newer generation. So essentially, it interprets the code to different machine code. So it depends on what CPU you're using, it will interpret to the correct machine code. So now, because of that, you only need to have one version of your source code. And depends on the CPU, you will just run the correct version. Kind of similar to Java right now, right? Doesn't matter whether you run your Java in a Mac or a PC or a Linux machine. All you need to do is to have an environment. And in that case, in Macintosh case, the environment is embedded inside the program. So you have a subprogram within the program that actually does the conversion or interpretation directly. And this kind of idea, we call that, or the process, we call that emulation. You are emulating the environment to run the program for you. So this is interpretation. So in general, interpreting language is a lot easier to write. Think about Java versus C or Python versus C. It's always easier to write because there are a lot of built-in support from the interpreter. So you don't have to really design your software based on the need of the hardware like C. And again, as I mentioned, so because interpreter is a program itself, so you can create a lot of mechanism to handle error to make the programming experience a lot better. And on the other hand, the performance of interpreter program is slower because you are using your CPU to do extra job during the runtime. So usually it's slower. So that's why we don't usually use Java or Python to do system or operating system job because it will slow down your system. But on the other hand, because the code is generally cleaner, so the program itself is smaller, the executable is smaller. Right? Not really executable, but the code itself is smaller because one line of code can probably do multiple work already. And one benefit of using interpreter language is that it's independent of what machine you're running, as long as you provide an environment. For example, MATLAB. As long as you install MATLAB in a computer, it doesn't matter whether you're running a Mac or PC, you can still run the program, okay, just like Java, right? But if you are using translation language like C, you have to recompile, and that's the problem. Okay. But in terms of translation or compiled language, it's always more or almost always more efficient because you compile the program into zeros and ones right away. So during the runtime, it doesn't really cost CPU extra load to understand what you're trying to run. Okay, so definitely you will use that for operating system. You don't really want to slow down your program. And also compilation helps us hide our program because now people cannot see your source code. All they can see is executable. So you can protect your patent maybe, or your intellectual property so that nobody can see how you implement certain algorithm. So that's what Microsoft been doing, right? So here is the step or other steps of how a program is converted from C to zeros and ones. So we kind of learned the individual process, but now we're going to study the complete process. So the moment when you type GCC, okay, to before you run the executable, what's actually happening inside the compilation. So yes, we always say compiler, but compiler actually does one job only, is to convert your C code to assembly language. That's it. It takes actually several other steps to complete the job of GCC, and we're going to take a look at it. Okay, so compiler, what does a compiler do? Compiler takes in a C file or any high-level language file, Java, C, C++. Okay. And it will process it and output the assembly language version of the C code. Okay. And this assembly language contains pseudocode or pseudo instruction, not pseudocode, which means that this assembly language is MAL, which is MIPS assembly language, because it contains pseudo instruction. And what are pseudo instruction again? Do you remember? Yes, any instruction that cannot be converted into 0 and 1 directly. For example, move, right? You have to convert it into OR instruction. Okay? So this is compiler's job. And we learned how to do that already. So I'm not going to talk too much about it. And the next process is assembler. Okay? So now you have the assembly language. And what does the assembler do? It takes in the assembly code, which contains some pseudo instruction, and then it will take care of the instruction and then convert them into object code. Basically, just zeros and ones with some extra information stored in some form of tables. We're going to talk about that later. Okay? And it will read and use something called directive. These are like internal instructions to tell the assembler how to read those assembly language instructions. Okay? And then of course, it will replace those pseudo instructions into true assembly instructions so that it can produce the machine code. And finally, it will create an object file that contains the zeros and ones of that particular file only. Okay? So not the final program yet, it's just the object file or the zeros and ones for that particular C file. Okay? And later on, we are going to combine all these object files into executable. So what are directives of the assembler? So basically, directives gives you the information about the instructions of the assembly language. So these directives, I'm sure you have seen some of them in your Merced programming already. So it contains, for example, text. When you say .text, anything after that will be considered as your assembly language code. And then you have another section called .data. These are the sections that you can declare variables, constant, so that you can use them in your assembly language. And there is another section called .global, and you can create symbol. When we call symbol, basically they are just label. Okay? And then since you declare them as global, other files can be able to access them. And this is called symbol. So as you declare global, then other files can be able to see them. Okay? And then you can create ASCII strings, which means that now these information will be stored as ASCII character. And finally, you can also declare words. How big is a word? 32 bits, right? So you can store them into a word size. And in this case, I have W1 to WN, which means that I have n number of words. So you can declare them differently. So it depends on how you write that, and then you can have this kind of symbol. Okay. All right, so pseudo instruction replacement. We kind of talked about that already, so I'm not going to spend too much time, but these are the examples that we can see. So sub u, okay, but you have a constant here, so it's not supposed to be sub u, and we don't have sub I, so we'll use NIU with negative. And this is a double. We didn't really talk about double, but double is a 64-bit value. So instead of storing them into one register, actually we need to store them into two registers. Okay, so consecutive two registers. You can see that the edges are 4 apart. And then multiple, we have to follow only 2 operands, right? Because I have the high and low. And then add U, but you have a constant, so it's not the same. And branch less than is not really a true assembly language. You should just set less than and then just not equal. Okay, so these are pseudo instructions. Okay. So how do we produce machine language? Okay, so from your assembly language. We kind of talked about the last lecture already. So let's review them. So if they are just simple cases, for example, just arithmetic, logical shift, those are format, just go ahead and convert them because you have the information ready. They are all encoded inside the 32 bits of instruction. Only when we need to deal with address, then we need to spend some time to analyze. For example, branching, right? How do we do branch? Do we need to know the actual address? Do we store the address inside the branch instruction? No, right? We use PC relative. We count how many lines away from the next line, right? And then put that as our immediate. So this is called PC relative. Okay. And so once we convert all the pseudo instructions into assembly language, the true assembly language, we can tell how many lines apart, right? So and then we can do the counting. So yes, this will be done in the assembler. Okay. But what if we branch to the future lines? Then how do we count how many lines? For example, here, when these two are the same, I'm going to branch to L2. But when the assembler is dealing with this line, it doesn't really know what L2 is. Right? It doesn't really know where the L2 is. So how can I replace this L2 with an integer? You cannot. So you cannot convert that into zeros and ones here. Right? So which means that the assembler has to wait. It continues to convert and convert until it sees L2. Now it knows that this is L2 and it starts doing the counting. You start from the next line and count 1 and 2. And later on, you replace this with 2 because you have 2, right? This is the next line. You start counting from 1 and 2, and you have the next line. So this is how we do the forwarding. So yes, it takes 2 passes. The first pass, you wait, okay? You know that, hey, I need this, so I'm gonna wait. Let's do the next few lines until I see this label. And next time when I do the second pass, I will fill in the number here, number 2. So this is 2-pass process for the assembler. Okay. All right. So what about jump? So jump, even though we know the address, but the thing is, the address is absolute, means that If later on when we combine the programs, the location of these lines will be different, right? So which means that I cannot actually encode it into zeros and ones because the address may not be the same. So this is something that we need to keep in mind. So now, which means that the assembler needs to wait. We cannot convert that into machine code yet. And we need to somehow jot it down and find out what address we need to fill in later. And this is something what we call relocation table. And this is something I'm going to talk about later. Okay. So for example, when we need to reference the data, right? So I need to load the address, right? But we don't know the data yet because when we combine, the data will be stored somewhere else, okay, in the whole complete executable. So now when we do the load address, the address will be wrong, right? So that's why we cannot actually hard code the address yet. We have to wait until we combine all the object code into one executable. Then we know the actual exact address. Okay. So in this case, I need to create two tables. Okay. So these two tables will be used to store the temporary information so that when we combine the files during that stage, the information will be gathered and then we will fill it in the blanks. Okay. So the first one is called symbol table. Symbol table basically is a table to list all the information that we have in our current file. For example, which line do we call a function that contains a jump, right? Or which line do we have the dot data, for example, starting the data section. So whatever we have, we put that into our symbol table. Okay? And relocation table is the opposite. Okay? We are going to jot down which line that we're going to need something else. Okay? For example, I have a line called JAL, but I don't know where to jump to at this moment because this function or this address may be out of my file, out of my current file. It may jump to another program, right? So I don't know the exact address. So now I'll put this kind of information into relocation table. So basically in relocation table is a table that stores what we are going to need. So later on, when we try to combine files, we will use the relocation table to find out what we need and then go to someone else's table, the symbol table to look for what they have, and then we combine them. So this is relocation table. Okay, so because the target address can be internal and external, and also any data. When we load the data, we need the address, and we don't know where they are yet. So this is something that we need to save in those two tables. Okay. So in object file, basically the object file is not really executable yet. It contains zeros and ones. You cannot just run it right away. Okay. So it contains a header file, tells the linker, the later on the process to combine files about these object files. What does it contain, right? So it tells where the text segment are, okay, where the data segment is, and the relocation information, like what you need, and the symbol table, what you have, right? And then some simple debugging information. Okay, so this is what being recorded in the object file. So when you have this object file and then during the linking section, you will be able to, the linker will be able to look into this information and then create a final executable. So for more information about the object file format, you can go to Wikipedia, not really Wikipedia, but go to this website to take a look at the standard format. So this format works for most of the operating systems except Microsoft. All right, so let's take a quiz. So in assembler, it will ignore the instruction loop no op. So remember, no op doesn't do anything, right? So since this label does not do anything, does that mean that the assembler will ignore this line? Okay. So it won't be translated into 0 and 1. Second question, Java designers use a translator and interpreter. So as I mentioned, hybrid, right? Mainly because ease of writing, better error message, and small object code. Is that true? Is it the main reason? So the first question, nope. So even though this line does not contain any instruction, even though no one doesn't do anything, but because the label is there, so the assembler still need to translate that line. It has to give a new address for that line because of the label. Okay. And also Java designer use the hybrid scheme not because of the easy of writing the program, but because of the portability, so that you don't have to recompile the program everywhere you run the program. So you can write a program, compile it into Java bytecode, and now you can run the same program into different operating systems. So it's for the portability, and that's why it's so popular to use Java to write apps, because you don't have to worry about the hardware as well as the OS, because as long as you have the Java environment and your program is updated, then you can run the program anywhere. Okay. So the answers for both questions are false. All right, so that concludes our lecture 15. And again, if you have any questions, email me as well as come to my office hour online, of course, as well as your TA's office hours. And I'll see you in the next lecture.